All right, everybody, hello and welcome back. Today what we're going to do is we are going to expand our discussion on quadratic functions, and we're going to talk about what is a new concept for us and a very abstract one, that is imaginary numbers. So to kind of set the stage a little bit, let's work on doing something we should be familiar with, and we are going to solve this quadratic. So we have 2x squared plus 8x plus 5 is equal to 0. Now, if we divide out a GCF first to make our job a little bit easier, we get x squared plus 4x plus 5 is equal to 0. Now, we could try to factor this, but we should be able to realize that there's no number that multiplies to a positive 5 and adds to 4. So instead, I'm going to use the quadratic formula. We have the opposite of b, plus or minus the square root of b squared minus 4 times a times c all over 2n. So if I go to simplify, we get a discriminant value of the square root of negative 4. And so therefore, our solution is negative 4 plus or minus the square root of negative 4 divided by 2. Now the problem here is, in our past unit, what we've been doing is every time we take the square root of a negative number, which we are ending up doing here, our answer would be no real solution. And if we connect that to what the graph of this should look like, that means we'll have no real x-intercepts. And now, although this is true, we need some way to discuss the solutions of this quadratic. There's a very important idea of polynomial functions called the fundamental theorem of algebra that tells us when you have a degree or highest exponent of 2, that means there has to be 2 solutions. Now, there's a lot of other things in math that is based off of this idea, so it needs to hold true for quadratic functions even when our discriminant evaluates to a negative. This is where our imaginary numbers come into play. So if we kind of just think about what an imaginary number is, think about numbers as a whole. We've got a big umbrella term, but these break into smaller parts. We have real numbers first, which include irrational numbers, such as the square root of 2 or pi or things like that, the square root of 5, for example. Now, we also have our rational numbers, and those are the numbers that can be written as a fraction. So we've got whole numbers, negative whole numbers, fractions, negative fractions if we wanted to, things like that. So this is typically the terms that we've been dealing with, the values of numbers we are familiar with. But there's another branch that make up our missing portion here that is going to be our imaginary numbers. And this is what we're going to talk about today. So by definition, an imaginary number comes from the idea that I squared is equal to negative 1. So I is essentially like the value e. Although it is a letter, it represents a known value. In this case, the definition is I squared equals negative 1, which tells us, therefore, that I is equal to the square root of negative 1. So every time we have the square root of a negative, we can simplify it by writing I instead. Here's an example of what that looks like. So we have the square root of negative 36, excuse me. We know that in the past we haven't been able to take the square root of negative numbers, so what we can do now is we can split this into 2 parts. We have the square root of 36, which we all know to be 6, and then we have the square root of negative 1, which, as we just learned above from our definition, is going to be I. So the square root of negative 36 simplifies to 6i. We can do something similar with a value that's not a perfect square, like the square root of negative 48. So we'll split this up into, first I'll deal with the square root of 48 and the square root of negative 1. And then we could break 48 up into the square root of 16 times the square root of 3. Well, the square root of 16 is 4, and we have our root 3. but we also have our square root of -1. So since the square root of -1 is I, the I is going to go outside of the radical and therefore immediately after our whole number, but before the root 3. So the square root of -48 is going to simplify to 4I root 3. And essentially what this just means is 4 times I times root 3. It is not much different than when we have 4 times root 3. The only difference is we now have a value I, which represents the square root of -1. So essentially, this definition that we have up here, I squared is equal to -1, lets us simplify the square roots of negative numbers, and therefore allows us to calculate and find the imaginary solutions of certain quadratics. Now, in this solving process, what we could do is with our new knowledge up here, this will simplify to -4 plus or minus. Well, the square root of +4 is 2, but because there's a negative into the square root, we have I over 2 as well, which will tell us our solutions are -2 plus or minus I. These are our two solutions, -2 plus I and -2 minus I. Now, as you can see here, this number is a little bit complicated. We've got a real number in the front and then an imaginary number at the end. This is what we call a complex number. And it's complex because, again, we have a real part, and then we have our b value, which is an imaginary. It's our imaginary coefficient. So the I just indicates that it is the imaginary part, and then the b will be its coefficient. So all these complex numbers have multiple parts. We've got -3 minus 2i, so the real number is 3. The imaginary is -2. It's a coefficient of I. We have a real number of 6 plus 3i, so 3 is our imaginary coefficient. And then we have this one here, which looks a little bit different, but realistically it is just 0 minus 1i, so the real part is 0 and our imaginary coefficient is 1. Now, we need to be able to graph these complex numbers just like we are able to graph regular numbers. So we have what looks like a typical coordinate plane over here, but we have to realize that we've got all real numbers are on that horizontal x-axis, as we like to think about it. And then instead of a y value, we have imaginary numbers. So we've got the real number plane, the imaginary number plane. Since complex numbers are a combination of real and imaginary, we are going to be somewhere on this plane. Let's take a look at our first example. We've got 3 minus 2i. Well, if we are going to graph that, what we need to do is go to the right 3, 1, 2, 3, and then our imaginary value is -2. So we're going to go down 1, 2 in our imaginary direction, and we will get a point right here. Now, some people do this, some people do not. What I typically like to do is I like to create this as a vector. And the reason it is a vector is because we are going to have both a direction and a size, which we will talk about later on. So when you are graphing complex numbers, it should be an arrow, which again is really just a vector. Over here, we've got our next number. Our next complex number, which is 6 plus 3i. So I'm going to go 1, 2, 3, 4, 5, 6 to the right, and then up 1, 2, 3. 1, 2, 3, 4, 5, 6, 1, 2, 3. So we're going to have a point right there. And now we're going to connect from our origin out to that value because, again, imaginary numbers are vectors. Lastly, we are going to graph our last piece here, which is really originally just -I, but as a reminder, it is still a complex number. It just has a 0 for our real part. What that means for us is we are not going to move left and right from the origin. Instead, we're just going to move in our imaginary number plane, and therefore we are just going to move down 1, and there is our vector. Okay? So, although this is a very strange, abstract concept for us, imaginary numbers shouldn't be overly complicated. Essentially, all it is a way for us to evaluate different polynomials that don't have any real solutions due to the fact that all quadratics should have two solutions. So we're kind of just extending our knowledge of quadratic functions. Instead of having situations where quadratics do not have real solutions, now we can simplify a little bit further and give some specific information about those quadratics instead of just saying no real solution. Okay, so this does take a little bit of time for us to adjust to. Imaginary numbers are strange to us because we've never heard of them before, but the more we practice, the more comfortable we will get. Okay, as always, thank you for listening. If you have any questions or concerns, please feel free to reach out.